So this week I'm gonna lecture on wood and wood construction. I'm gonna go through the principles of wood, some of the different aspects of wood construction. We're going to talk about timber framing or mill construction, and then we're going to talk a little bit, start talking about light frame construction or residential style construction. Wood itself has a lot of different components to it, and when we're building with wood, we need to think about the fact that it's a natural material. It has defects in it. It has insect damage. It could have a little bit of rot here and there, or some defects that would cause it to not necessarily be as structurally strong as the next piece of wood. So, with that in mind, we need to just think about designing to make sure that it's kind of like designing for the weakest link. You're only as good as your weakest component. So we want to look our wood over good and make sure that we've got good quality product. Most of the stuff you've heard before in your biology classes. The outside protective layer is the bark, and inside the dead bark is a layer of living bark called the cadmium. And that all that material kind of is what brings the nutrients to the trees. The thick layer of living wood cells inside the cadmium is the sapwood, and that's where the nutrients are stored. The energy is stored in there, and then in the center, of course, we've got the heartwood. At the very center of the trunk, surrounded by heartwood, is the pith of the tree, a small, weak zone of wood cells that were the first year's growth. All wood is pretty much cellularly the same. We have softwoods and we have hardwoods. Softwoods come primarily from coniferous trees, coniferous meaning evergreens, cone shedding trees. Your hardwoods are your deciduous trees being the ones that normally would lose their leaves in the fall. So this is a list of the softwoods, everything from firs to spruce, pine, hemlock. We've got some of the softwoods we use for moldings and frames are pines. Used for finished flooring, we've got fir and longleaf pine. We don't use that too much anymore. And then we've got our decay-resistant woods, which are cedars and cypress. Normally you find that material growing in swamp or wetlands. So it's relatively decay-resistant because of where it grows, and it's lightweight, so it holds up well. Your hardwoods used for moldings, paneling, and furniture, everything ash, beech, birch, black walnut. You can go through the list yourself, but those are, and some people, poplar, for instance, is considered a hardwood, even though it's probably one of the most softest of the hardwoods themselves. Grows rapidly. It does take the paint well, so it's used a lot. It doesn't have a lot of grain, so we use it a lot in our shops for molding and whatnot. And then finished flooring, of course, your maples, walnuts, oaks, and pecans. They don't mention birch here, but we use a lot of birch for finished flooring also. Putting the logs through the lumber mill, we cut our logs in different ways. We have plane sawing, and our sawyer would look at the log depending on, you can see how the grain looks different. When you look at the top of a piece of lumber and you see this type of pattern, it's generally from the log being plane sawn. Quarter sawing is kind of keeping it's a little higher quality because it keeps all the grains straight on the wood, which kind of allows the wood to shrink more uniformly. You don't get the warping and twisting that we'll talk about here in a minute. And then there's the typical sawing of a log for possibly structural, where you can get your 2x4s and your 4x8s, and you're looking to get the most product out of the log itself with the least amount of weight. So these are just different ways that the sawmills might look at it. Now, I've highlighted this area up here. Solid lumber has an embodied energy. Remember, embodied energy is the amount of energy that it actually requires to get that piece of wood into the building. It says it has an embodied energy of roughly 1,000 to 3,000 BTUs per pound. An average 8-foot long 2x4. I think you pay about $3 for it in the lumber yard or at the Home Depot, maybe $4 if it's really good quality. Has an embodied energy of about 17,000 BTUs for that one 2x4. That's 17,000 wooden kitchen matches of energy, which seems like you could just as easily use the kitchen matches, but that includes the energy expended to fell the tree, transport the log, saw and surface the lumber, dry it in a kiln, and transport it to the building site. So it requires quite a bit of energy to just create one 2x4 and get it to the site. It's very recyclable. Whoops. The other thing that we do with wood is make sure that we get the moisture content down by putting it into dry kilns. You can let it season. When we talk about lumber being seasoned, that means it has its moisture extracted to the point where it's no longer what we would consider green. Kiln drying is where we're kind of forcing it in. We're putting it in a heated shed where the moisture is extracted and taken away. And it's done in a timed fashion so that the wood will shrink uniformly. It's designed so that a lot of times they'll build kilns and use the waste wood as heat to try to, save energy. But kiln drying at the lumber yard is done a couple different ways. Wood, as it dries, will shrink, and it doesn't shrink uniformly in all directions. It shrinks the least in its longitudinal. In other words, the length of a 2x4, it would shrink the least amount in that length. Shrinkage in the radial direction, which is, I believe that's perpendicular to the grain, is very large in comparison. And shrinkage around the circumference of the log, tangential shrinkage, is about half again greater than radial shrinkage. And we can see that illustrated in this next illustration, where we can look at the log and we can see how this would dry. We can see that tangentially parallel to the grain, we see that this wood is shrinking more in this direction. And if the wood is cut along this bias, we can see that it's going to shrink a little bit differently. If it's along the grain that's kind of bias or at an angle, we're going to see kind of this cupping type shrinkage. So we need to be able to control that because wood does shrink differently in different directions. And I would say perpendicular, you can see in this circular one how it's this is tangential, and radial would be parallel. So this one here, this illustration here, I think is a little off. This is more in line, where it's going to shrink more against those lines that produce the wood grain, and less when it's parallel to the wood grain. When wood is surfaced, it's planed. In other words, it comes out of the sawmill. A 2x4, for instance, would be 2 inches by 4 inches, and then it's planed down. So when we buy a 2x4, that's a nominal dimension. What we get is a 2x4 becomes not 2 inches by 4 inches, it becomes 3.5 inches by 1.5 inches, because we surface that off and make it smooth. We can see on a grade stamp it may say S4S for surfaced 4 sides, or S2S, surfaced 2 sides. Most often we'll see S4S. Now there's 2 indications on a grade stamp, and we see that indication down here. This is the American Forest Products Association, mill number 27. It's a grade 2 piece of lumber, spruce, pine, or fir, and it's S dry. S dry in the lumber grade stamps indicate that the piece was surfaced when in a seasoned dry condition. S green indicates that it was planed when green. So what's the difference? What could be the difference? S dry is more expensive, because what happens is it comes out of the the sawmill, green, goes in, has to be transported to the dry kiln, gets dried, comes back out, then goes through a planer mill to plane it down to its actual size. More steps. S green, it comes out green, it gets planed, it gets taken to the dry kiln afterwards. And so it's less steps, less expensive, but more option for the wood to actually curl or shrink or become crooked, like some of these pieces of lumber you might pull out of some of the larger big box lumber stores get a little bit warped and twisted. We can see some of that here where the wood can crook, it can cup, it can twist, it can bow. So all of those things can happen. If we were to put a piece of pine on a wood base and it's not completely dry and we put paint on it, we might, when you look at the end of it, you'll see that it's actually cut out. It has a relieved back on it. So if it shrinks and cups in, it's not going to split the wood. It gives it a little bit of give and allows it to move within the woodwork. Otherwise it might pop itself off the wall. So you'll see some of this stuff built into the wood, so it allows for a little bit of additional shrinkage as the wood moves along. Now here's a chart showing lumber sizes. S4S again means surfaced 4 sides. The dimension, nominally 2 inches by 2 inches, would actually be 1.5 inches by 1 9/16 inches. Or actually just 1.5 inches by 1.5 inches. 3 would be 2.5 inches. A 4-inch thick piece of wood would be 3.5. So if it was a 2x4, 1.5 inches by 3.5. If it was a 2x6, 1.5 inches by 5.5. And you'll notice this line right here. There's no line, but I'm making an imaginary line between a 2x6 and a 2x8. Suddenly when you get to 2x8s, we're increasing the surface planing. And a 2x8 is actually 1.5 inches by 7.25 inches. And it stays that way all the way up through. Anything over 12 inches is still 3/4 of an inch smaller than its actual dimension. So a 2x12 would actually be 1.5 inches by 11.25 inches. Anything larger than 5 inches we refer to as timbers. So rough or S4S shipped unseasoned 5 inches larger is just 1/2 inch off the nominal size. So a 6x6 would be 5.5 by 5.5 inches. And then we have decking. We have also sizes. 2-inch decking would be 1.5 inches thick, and it basically plays the same role here. It's a 1/2 inch smaller when it gets planed out. We measure lumber by the board foot. A board foot is 144 square inches. It's a board foot, 12 inches square, nominal cross section, and 1 foot long. So a 12 inch by 12 inch by 1 inch piece of wood would be 1 board foot. A 1 by 12 or 2 by 6, 10 feet long contains 10 board feet. A 2 by 4, 10 feet long, would be 6.67 square feet. So it's 2 by 4 divided by 12 times 10 equals 6.67. Or you can just take the total cubic inches and divide it by 144, or 12 by 12, to give you the number of board feet. Now, we don't purchase lumber as much by board foot anymore. You don't go in and say, I need 100 board feet. A 2 by 4, the sales clerk would probably look at you like you're crazy. A carpenter, on the other hand, would know board feet. They may measure it. Sometimes if you're buying in bulk, you're buying by the board foot. So as you're estimating and putting things together, be cautious to know whether they're talking board feet or linear feet, because it does make a difference. A 2 by 4, 10 feet long is only 6.67 board feet. So you don't want to overprice yourself or undercut yourself by mistaking that. We're going to get into some manufactured wood as we talk about wood framing. This is an LVL, a veneer plywood type lumber section. used for beams. We'll see some other ones here. This is using a PSL. This is PSL is a position strand lumber, where all the lumber, the strands are compressed and put into one beam. It has fiberglass or reinforcing within the glue sections to give it strength. That's used in very long spans in residential construction where we need a lot of support. Garages underneath, for instance, we see a lot of this, and up above we see this this LVL type construction. Whoops, did I miss one? No. So we use a lot of manufactured plywoods, and plywoods can be, of course I always call this one regular plywood. We've got plywood, which is laminated veneers running in opposite directions for the grain every other layer. They're generally odd numbered layers, and they have a lot of strength in all directions because of that turning of the grains. Then we have composite panel, which is a veneer on top and bottom and a particle board type core on the inside. We have wafer board, and below that, lost my mouse, we have oriented strand board, OSB, and then at the very bottom we have particle board, which is basically compressed sawdust with glue and other types of epoxies. Plywood itself, as a decking material or roofing material for structural strength, has what's called a span rating. So when you look at a piece of plywood, you're going to see a grade stamp similar to what we saw on the lumber, which indicates that this one has a span rating of 24 inches on center. Now you'll notice some of these have two span ratings, 48 and 24. The first span rating indicates that if it's used on a roof, it can be at 48 inches on center. But if it's used as a flooring material, it can only be 24 inches on center because of the weight distribution. So that dual span rating indicates whether it can be on an incline. The first one is your roof. The second one is your horizontal floor framing spacing. So you need to pay attention to these stamps when you're looking at structural plywoods and composite boards. We use a lot of pressure treated lumber for decks and sills and whatnot. This is just an illustration here of what's called incising, or what are called incising marks, which are used to pressure impregnate the wood preservative into the wood. So most of your better pressure treated woods, when you look at the tops and bottoms, you'll see these little teeth marks on them, and what they're doing is actually digging into the wood with these teeth and injecting the preservative deep down into the grains rather than just painting it on the outside. So when you see those, it isn't a defect in the wood, it's actually how they put the pressurized preservative into the wood material. We're going to talk a little bit about fasteners. Nails, to start out with, our most common fastener, are sized in pennies. It uses a D letter. So the origin of a 10 penny nail or a 5 penny nail comes from the fact, or is thought to be an explanation, that it was the price of 100 nails of a given size. So back in the early days of nail manufacturing, I could buy 100 of this size nail for 7 pennies. I could buy 100 of this size nail for 10 pennies. Or I could buy 100 of this size nail for 60 pennies. So the larger the nail, the more expensive. Now we sell them by the pound, so it's not such a big deal. But the term penny is still, if somebody says, get me some 16 penny nails, they're 3.5 inches long. So I'm not sure if the boxes still refer to them in penny size. I'm sure they do on the outside. So carpenters will refer to these in penny sizes. But that is the explanation of the origin of the size for those nails. Nails are put into wood, pounded into wood, either face nailed, end nailed, or toe nailed. Toe nailed being at the angle. Other types of fasteners, we have lag screws, drywall screws. I build everything with drywall screws. Regular wood screws, slot heads, round heads, and oval heads. On this side, we have machine bolts, which have a hex head on both ends. And then we have a carriage bolt. The carriage bolt has a square nub on the bottom, so it can have a hole drilled. Use a hammer to pound this into the wood, and that's what holds this end of the bolt while you tighten it up on this end. And if your hole's not too big, it won't twist around. So the difference between a machine bolt and a carriage bolt is just the opposite head. Should be hands-free. Just looking at this chart on fasteners, these are the different types of heads that we might see on a screw fastener. Everything from flathead with ribs, bugle head, trim head. You can actually buy screws that are for finish work. The threads are either coarse, fine. These are high-low threads. I've seen those a little bit. Some twin threads. They all have to do with the holding power and what type of material it's going into. And the points can be sharp, drill points, pilot points, or drill point with wings, where they actually self-drill their own pilot hole to prevent the wood from splitting as it's going through. So we see a lot of these screws being used in raw wood. Other types of fasteners that we see used on pre-engineered trusses, for instance, would be these toothed plates, which are just, this picture doesn't show them, but you'd actually have tooth plates at all these joints holding the wood structures together. So we see a lot of pre-engineered wood trusses being manufactured. They're quicker, easier, and less stress getting them up in place. So it's just less reliability, liability, I guess, if you're using pre-engineered trusses. A lot of times, buildings that are constructed pre-engineered off-site in a protected building, in a climate-protected building, can be built much stronger. For one reason, they're built in a protected area. The other reason is they're built to be transported across the road and not shake apart, so they have to be a little tighter. So from that aspect, sometimes your modular homes aren't as, they're less expensive because they're manufactured, but they're really, the construction itself is designed to hold together over the road. Hopefully not today's roads. Some other hangers. We've got joist hangers here that are used to hang floor joists. We've got beam hangers, top caps on post. Some of these are designed. We have hangers that are used for hurricane force winds to keep walls from uplifting. Just anchors that will hold things in place. These rafter anchors, for instance, are used quite extensively in the light frame building construction. Some manufactured I-joist, used a lot in long spans, residential homes instead of the larger lumber. These are probably now more economical than trying to find structural lumber that is at the same depth for the same strength. And then we have what we call pre-engineered panels, building panels that you find in the modular home industry. But we use these a lot as these structural insulated panels. You hear the term SIPS panel, S-I-P-S, on the job site. When we talk in a minute about timber framing, a lot of these SIPS panels are used to cover the outside of timber framed building constructions. Now let's talk about heavy timber frame construction, and it's also known as mill construction. We think about heavy timber frame construction, we think of the nice home with the beams exposed on the inside. But it also includes some of the mills. If you're down in New Hampshire, and Lewiston, Auburn has a lot of these old textile mills that are built from heavy timber frame construction. Heavy timber frame construction, or HT as it's referred to in the fire rating book, is more fire resistant than light wood frame construction because the wood is so dense. On the beams themselves, you'll notice that the edges are sliced off to make them less flammable. They have chamfered edges on them. We see typical construction of a wood frame residential type building where they're building these frames on the ground. In the old days, of course, they'd have a barn raising. They use what they call pikes to stand these. These layers of wall framing are referred to as bents. and these bents would be stood up in place as the walls go up. Here we can see those bents all up in place and locked in. And on this bottom photograph, you'll actually see these structural insulated panels being applied to the top of the roof and the walls to provide a thermal break free thermally unbroken insulation skin for the outside of the building. So from that standpoint, they become very well insulated, although more expensive than your normal light frame construction. Here's some typical mill construction. We can see some of the things that are involved in mill construction. We see these heavy beams and columns running across the floors. The floors are actually tongue and groove, thick wood paneling. We can see this one actually probably looks like it has some sprinkler heads in there. But some of these old mills that were put together stood for many years, and if they did catch fire, a lot of times they were put out and the structure itself was still in good shape. They would char the outside of the wood, but they'd continue to use the structures. Here's some of the components of mill construction. We can see the brick exterior. We have roof girders and we have roof beams. The girders usually support the beams horizontally. Then we have our columns. You can see that the columns are chamfered on the edges to make them less or more fire resistant. We have these wall straps that will hold things in place, these wall anchors. Pinning the floor beams together, as well as the roof beams, are what are called iron dogs. They're basically staples, large iron staples. Because of wood shrinkage in between the floors, we would have this cast iron column support that goes down. It looks like an hourglass, fits on the top of this other one, and that's referred to as a pintle, P-I-N-T-L-E, and that would go all the way down through the floor. You'll see these holes out through the brick. If you look through some of these old factories, you'll see these holes. If there was water, flooding of any type that would come in, rather than having it sink the floor, we have these scuppers. Scuppers allow water to escape out through the wall and prevent it from building up on the inside. So there were, even in the old days, there were certain safety devices built into these types of structures. So you can kind of print this out and keep an eye on some of these major items to be able to identify them. When mill construction was first put in, they used to just make these pockets for the floor joists and beams to go in, and then the decking would go on top and it would be square cut. And if the building did catch fire on the inside, and imagine if this floor was burning and all of a sudden it burned through and started to collapse, what would happen is this edge of the floor would actually kick up and knock the brick over on the outside. And I'm sure some firemen probably lost their lives being crushed by falling brick walls off of these buildings. So a fire cut was developed, so when these beams get put in, they cut this beam at an angle, so if the floor does collapse, the outside wall will still stay intact and structurally sound, so that the masonry is probably, it may be fine and the interior could still be rebuilt, and that's referred to as a fire cut. Here's an example of a large, heavy, timber-framed building. It's a laminated wood dome that spans 530 feet, covering a 25,000-seat football stadium in Tacoma, Washington. So there's not a whole lot of limit, depending on the size and the ability to put these things together, as to what you can build. I'm not sure if this is still up or not, but I thought it was kind of an interesting photograph of a large timber frame type building. Now let's talk about wood light frame construction. Wood light frame construction is our bread and butter. We've all helped somebody build some type of structure, whether it was a dog house or a bird house. We know how these things are put together: 4 walls, a floor, and a roof. light frame construction started out on the right in what's called balloon framing. Balloon framing is a vertical stud that goes all the way from the foundation to the underside of the roof deck continuously, because we used to be able to get 20-foot, 24-foot 2x4s. And then there would be a cleat put into the wall, and the floor framing would be put in. Similar to timber framing, and kind of a cross of the timber framing, as heavy timber became less available and people were able to saw lumber into much smaller pieces, it became easier to handle. But building a structure like this with balloon framing has its disadvantage in that it takes more than one person to be able to lift all this stuff into place. It still ends up being kind of a barn raising to build these things. And the walls themselves had a tendency to be fire spreaders in that they formed chimneys. So blocks of wood had to be put in between each stud on the way up at the floor levels, called fire stops, to keep that draft from creating this this high fire danger. So as it was developed, the other method that's more common today is what we call platform framing. And platform framing basically starts at the foundation, sill plate, they build the floor structure, gives them a working platform to work on. They can build the first floor walls, construct the second floor platform on top of that, then construct the second floor walls, and then construct the roof on top of that. The advantage being that the framing becomes much easier to handle by one person. One person can build a home all by themselves for the most part, maybe with the help of some chain falls and some lifts, but much easier to handle. And this was all developed, all of this light framing was developed during the time when sawmills were going up along rivers and manpower was scarce. It was actually, if you look at the dates, in the 1860s, it was during the Civil War, so people were kind of scattered. We didn't have the people on the farm, so this light frame construction became the popular way to build. Here's an illustration starting with the foundation. We build our platform, we've got our wall construction in columns, we build our other platform, second floor wall construction, build your roof on top, and you've got your enclosure. Pretty simple. Just a little aside, kind of an interesting aspect. What you're looking at here is if you're going to dig the foundation for any type of building, these boards on the outside are referred to as batter boards. The batter boards allow us to set up on the outside, and we'll lay strings across that. Where these strings cross would indicate the corners of our buildings. We can then bring in an excavator, excavate this hole. Now, if we just put stakes at our corners, what would happen when we excavated it, we'd lose our marks. So these are set back far enough so an excavator can get in here, dig out around, and then if we want to re-establish where our foundation is, we just reattach these strings and we have our foundation laid out without having to crawl around inside a hole. So it makes it a little easier to reestablish the shapes of our buildings using batter boards on the outside. Just if somebody says we need to put some batter boards up here, it's a good term to know. Here's some typical framing, and we'll probably in some future lectures talk more about the intricacies of light framing and some of the different names that we're going to be looking at. This is a framed wall opening. We generally have a single sole plate sits on top of the floor framing, or the floor deck. Here's a sole plate. We have our studs coming from the floor to a double top plate, two 2x6s or two 2x4s. This is a header across the window opening, which gives us our structural ability to span a window opening without putting any pressure on the window or door itself. We have a rough sill, which our window would fit in on the bottom. These support studs on either sides, sometimes people refer to them as jack studs, and sometimes these are referred to, I believe, as jack studs also. So we got our sill, We got our jack studs, we got our header, and then these little spacer studs in between the top plates and the header are referred to as cripple studs. The header itself is just a sandwich, could be 2x6s, 2x8s, 2x10s. To make up the wall thickness, it could just be two 2x6s, and this one actually has a half-inch plywood on the inside to give it a good strong header. Other aspects of light framing, we can see our wall studs. I put this picture in here just because I think we don't hear these terms often. When we see an overhang on a gable roof, these spacers are referred to, these cantilevered framing members are referred to as lookouts, meaning it's giving you an overhang on the roof itself. And the rafter that's on the outside edge of these lookouts to give you the overhang is referred to as a fly rafter. Again, another term that's good to know. We've got our regular rafters in here that have bird's mouths on them to set over the top of the double top plates. The fly rafter does not, because it doesn't have a wall to set on. It's being supported off these lookout framing pieces on the outside. Speaking of roofs, we have a number of different shapes that we can look at. We have a flat roof, and we don't really refer to these as flat roofs as much as we refer to them as low pitch roofs. Most of your manufacturing buildings out there that look like they have flat roofs are actually low pitch roofs. We have a shed roof, which just has one slope, front to back or side to side. A gable roof we're very familiar with. We have two slope sides on it. Then we have a hip roof, which has slopes on all four sides. We have a gambrel, looks like a barn roof, where it has a steep side pitch and then a lower top pitch, creating areas for rooms up above and these knee wall sections. And then this last one is referred to as a mansard roof, which has actually 8 pitches. 4 pitches, 4 pitches, 8 pitches. So it's like a hip roof gambrel, or known as a mansard. So those are just some of the things that we can talk about in wood framing and light frame construction, or how these things are put together. There's a lot of other things. I may put some stuff together later on. It's all part of still division, I think it's division 6 in CSI. And I think next week what we'll do is we're going to start talking about specifications and how they're written and put together. So once we get through this framing section. So as part of next week, we'll be talking about this as we start building our own light frame construction in the Revit program. So that will do it for this week's lecture.